Hello and welcome everyone to CS-412 Software Security, OX00 Introduction. This is the online version of the class and does not include any of the additional memes, details, and discussions that we're going to have on site. This includes a bare bones speed run through the slides, but focuses on the main topic. So you should get the main points of this class. Let's start. The learning goals for today are pretty simple. First, we're motivating the need for software security, and then I'll give you a quick overview of the class topics that will show up in the next couple of weeks. We're going to discuss scheduling of labs, classes, and exercises as they will show up, and where and how to get help. Let's start with the motivation. A basic fact of life is the software has bugs, and software has a lot of bugs. As mentioned by Microsoft, 70% of all security bugs are memory safety issues. So these are low-level bugs that are present in systems code. And similarly, on Linux, bugs are pretty frequent and show up in all the different places. When we look at Sysbot, this is a large fuzzing cluster that continuously tests the Linux kernel source code for any kind of vulnerabilities. We discovered that right now there's 945 open and unfixed vulnerabilities out there. So these are bugs that have not really been fixed yet and could potentially lead to any kind of security issues as we move along. So as we see here is that bugs are plentiful, bugs are everywhere, and they can result in any kind of severe security vulnerabilities, allowing an attacker to take over. As many of these bugs are actually exploitable. What do we mean with exploitable? An exploitable bug could allow an attacker to, for example, escalate their privileges from a browser to the operating system, and then from the operating system to the hypervisor to, for example, spawn a calculator, as has been done in the demonstration on the lower right. Here, a Windows virtual machine was exploited to gain access to the Windows kernel and then access to the host platform to then spawn a calculator. Other bugs are used to, for example, ransomware, encrypt all your personal files, and then allow an attacker to steal them and ask for a ransom. But it's not just desktop software and server software is being attacked, also IoT is being attacked. For example, in an industrial control system, the sprinkler could be turned on. Our physical spaces could be invaded by an attacker gaining access or unintended access to them. Or last but not least, the smart vehicle that we are driving could be turned into a remotely controlled toy vehicle, which may be a lot of fun for the attacker, but not as much fun when you're sitting in this vehicle driving into a ditch, right? So fact number one, software is full of bugs. Fact number two, many of these bugs are exploitable, which we have to work with and live with. Fact number three is that software is incredibly complex, and we are seeing a continuing exponential increase in complexity. For example, Google Chrome consists of 76 million lines of code. GNOME, the windowing manager, adds another 9-10 million lines of code. The windowing system, another million lines of code. Just the basic runtime system adds 2 million lines of code, and the Linux kernel clocks in at another good 17 to 20 million lines of code. This all means that we have over 100 million lines of code of complexity to look at cat pictures over the internet. Now, I don't know about you, but I actually have a fairly hard time assessing how complex or how hard 100 million lines of code is. So let's actually start with an example of this complexity. And here we have Margaret Hamilton with the code for the Apollo guidance computer. And this picture was taken in 1969, so quite a couple of years ago. And back then, code was written in assembly, so this was fairly sparse. So you had to use a lot of code to express a few basic concepts. And let's say, if you're generous, it took about 2 meters of complexity to fly to the moon, right? If we look at all the stacked up source code here. And this includes a lot of documentation, a lot of details, a lot of test vectors, and so on, right? So 2 meters of complexity to test and run the code that flies a spaceship to the moon. Now, if we print the source code for Google Chrome and the operating system at about the same density, we end up with a stack of almost 400 meters, right? And the stack is growing by 50, 60 meters each year, right? So this is a massive amount of complexity. Also, there's a massive amount of churn. For example, out of the 17 million lines of the Linux kernel, around 500,000 lines are changed each year. This means that code is continuously growing in complexity, but also existing code is changing. And now if you imagine a stack of 400 meters of complexity, and you're looking for a bug on a single line on one of these sheets of papers, right? So this is incredibly challenging and the complexity is mind-boggling. Now we need to develop tools and technique to handle this amount of complexity and to actually scale with the rise of frequent changes and of the complexity that the software brings us. So what are some of the key research questions in software security? Well, the very first research question is that we efficiently need to detect kind of security violations. And here at the bottom center, we actually have a source code snippet with a vulnerable function in there. And the first research question says to efficiently detect these violations by, for example, checking if something bad actually happens. Right? So instead of running string copy, we could check if the supplied buffer is of the correct length. We may want to automatically generate test cases for this vulnerable function that is in there by calling it with different parameters that we may have inferred from the rest of the code to test constraints and whatnot. We need to develop techniques that actually scale to large source repositories. Right? It's not a single file usually, but often hundreds, thousands, tens of thousands of files with many thousand classes and millions of lines of code. We also have to effectively test complex interfaces, such as when we are crossing from one system to another system by attaching a USB peripheral, right? So this is an interface that is being used to transfer data back and forth. And in addition to that, we have to mitigate some kind of defense, or we have to create mitigations or some kind of defenses to mitigate any kind of remaining attack vectors, right? While in the first 4 research questions, we're trying to understand the complex behavior and find and remove as many bugs as possible. As the 5th research question, we're kind of shifting the goalposts a bit and trying to mitigate any kind of remaining threats that remain in the code. Given the fact that due to the complexity, due to the large amount of code, and due to the high churn, we will never be able to find and fix all of the security vulnerabilities that are in the code. This is pretty much what we are doing in my research group here at EPFL. And I'm showing the pictures of all the bright students I had the pleasure to work with. The bottom row shows PhD students that have graduated in my lab. The top 2 rows shows the current research scholars, academic visitors, PhD students, and postdocs that are working with me and that I have the pleasure to advise. And we are working in 3 different areas of research. First of which is automated testing, where the goal is to get rid of as many bugs as possible. So this is a tool for developers that allows them to target their code and find and fix as many of the vulnerabilities as possible. And here some of the keywords are fuzzing, which is an automatic testing approach to discover bugs, and sanitization to detect the bugs when they are being triggered. Using the information that we have learned from this automated testing is we apply mitigations. And mitigations is an additional safety measure. Like, think of it as an insurance that you're applying on your code. Whenever code is being shipped to a user, mitigations make sure that any kind of remaining vulnerabilities are being stopped. Right? It's some kind of a last line of defense. And here we're looking at control flow integrity and type-aware data guards to protect the users from any remaining threats. And last but not least, we've recently started looking into compartmentalizations, where safe compartments break large complex systems into smaller fault domains, where we follow a divide and conquer strategy towards security, where we will have small safe components and then safe abstractions to interact between the different components. Now, having said that, I hope all of you join the Software Security Fund, right? It's an extremely fun research area, and bugs are ubiquitous and luckily a regrowing resource for us. So there's always additional interesting research to be done. We need to work on software testing to weed bugs out early before they can do any harm, customize mitigations to stop large attack classes and to prohibit the exploitation of any of the remaining attacks, and compartmentalization to limit the potential impact of these remaining bugs and issues. Our research in my group focuses on specializing fuzzing to new environments, enable developers to understand and build on the bugs and bug information, customize mitigations on a per program basis, and to infer strong compartmentalization mechanisms. And there's a bunch of PhD students working on all these fun topics. If you're still looking for a bachelor or a master thesis, I hope most of you are looking for a master project, do check out the EPFL project page and check what is still available, and do contact the students directly. If you're interested on the hacking side, I also would like to encourage you to join the EPFL CTF team. We're called the polyglots because we speak multiple languages. We talk C, assembly, binary code, Haskell, whatever you want, you name it, and are one of the top CTF teams. Capture the Flag, if you don't know it, it's a competitive security game. It involves real-world attacks where you play a game to solve challenges, score points, and capture flags. There's going to be more information later in the course, but it's usually an extremely fun game to play, and we also sponsor our team so they can go to DEF CON, which is like the World Championships of CTF, where they can go and play with the other top teams. Now, the outline of the course, we're going to talk about different topics. First, we're going to breeze through the secure software lifecycle, security policies, just understanding the basics. Then we're going to spend some time on attack vectors, where we will understand adversaries and where the different issues come from and how they can be exploited. Mitigating attacks is next, where we protect against the exploitation of bugs and also learn to the limitations of these existing mitigations, followed by automated testing, where we try to find and remove as many bugs as possible. We'll then dive into case studies on browser, web, and mobile security. You've all had security courses before, but let's start with the basic definition of security. Security is the application and enforcement of policies through mechanisms over data and resources. And the two words I would like to focus on here is policies. This specifies what we want to enforce, right? Like what we want to protect and what is actually being applied. And then mechanisms, which specify how we enforce the policy. As in, a mechanism is an implementation or an instance of a policy, as in a way to actually apply the policy to a given source space or system or whatnot. If we crystallize this a bit towards software security, then software security is the area of security that focuses on testing, evaluating, improving, enforcing, and proving the security of software. And we will discuss in detail the testing, evaluating, and enforcing aspects, and at least touch on improving the security of software. Especially given the large amount of scale, proving software will be difficult, and improving software focuses a lot on software engineering aspects, which we will try to minimize in this course. There's dedicated software engineering courses for that. But why should you actually care about security? Well, security is important, should you not have noticed it, Right? I don't think I need a lot of motivation for this, but I still want to give you just a couple of highlights of issues that I found just in the last couple of days pop up. Right? There's articles in top newspapers talking about different kind of security issues, both in low-level software, as in cyber risks in the Washington Post, or crypto issues where a lot of virtual money is being stolen based on bugs in given software, right? Additionally, attackers can use the vulnerabilities that we will talk and discuss on to obtain passwords, access to personal data, and then abuse this data going forward. And one of the issues that we will see is that nobody can write perfect code. Everybody will have bugs in their code. Even the most worst and best possible programmer will have buggy code in time. And this is perfectly fine, right? In software security, one of the things we will learn is that we have to anticipate the existence of bugs. There will always be bugs. We have to develop techniques to find as many of them as early as possible and get rid of them as quickly as possible. And then we have to make the exploitation of any remaining bugs as hard as possible. Now, you may ask, what is the reason for all these security breaches? And in a nutshell, it's humans. Humans are terribly bad at assessing risks. Like, should I enter my personal password into this form? Should I tell the stranger my username and password? Should I reply to this email from a prince that claims that they want to give me money? Right? Humans are incredibly bad at assessing cyber risks because it's somewhat of a new area for us, and we are having difficulties figuring out the issues and the potential threat vectors to that. As it turns out, developers are humans too, right? And even if they are using some smart code software like ChatGPT or Copilot by OpenAI, they're still, like, code is predominantly written by humans. Or even the software helpers are actually inspired by code that was written by humans. And the developer is responsible to ensure the security of the system, the security of the source code, and a safe configuration of the environment where the software actually runs in. The dominant programming language is C and C++, which most of the low-level code that you're running is written in are neither memory nor type safe. As in, your browser is written in C++. Your operating system kernel is written in C. Right? Here, the developer is responsible for all the safety checks. Root causes of the bugs that are exploitable could be out-of-bounds errors, use after free, integer overflows, or type confusion. And the consequences of these bugs could be code execution, where an attacker gets access to your system, privilege escalation, information leaks, or simple denial of service. Now, what actually is a software bug? And I simply refer to the definition on Wikipedia that a software bug is an error, flaw, failure, or fault in a computer program or system that causes it to produce an incorrect or unexpected result or to behave in unintended ways. Bugs arise from mistakes made by people in either a program's source code or its design, in frameworks and operating systems, and by compilers. Right? So this is the potential source of software bugs. Now, what is the difference between a bug and a vulnerability? Well, a software vulnerability, or all the software vulnerabilities, are a subset of the software bugs. So a vulnerability is a software weakness that allows the attacker to exploit a software bug, right? So this is a slightly different perspective. The attacker will be able to reach the bug, trigger it with attacker-controlled data, and then modify the outcome of the execution to the attacker's advantage. A vulnerability requires three key components. The system is susceptible to the flaw. Well, the bug needs to exist. The adversary has access to the flaw, for example, through the information flow by providing data that actually reaches the bug. And the adversary has the capability to exploit the flaw, for example, by knowing a sufficient amount of details around the environment of the program. For example, what system it is using, what C library it is using, and whatnot. That will depend on the customization of the attack. Software engineering is not equal to software security, right? And I would like to distinguish software engineering from software security a bit. This is not a software engineering class. Software engineering aims for dependability, producing fault-free software, productivity to deliver on time within budget, usability to satisfy a client's needs, maintainability, extensible when needs change, and so on. Software engineering combines aspects of programming languages, networking, project management, economics, and human resources. The existing or standard software engineering security is often secondary and frequently limited to some form of testing. Right? What we are discussing in this class are the fundamentals of software security, and we aim to bring software security into into light and make it a primary citizen, a first-class citizen of software development. As future software developers, you should all be aware of the security considerations that you are facing. To get you a better perspective of bug and buggy behavior, I usually introduce this using the Morris worm. And the Morris worm, this was a worm that was released on the internet in 1988 that took down the majority of computers on the internet. Right? A tiny 99-line program killed a large amount of the internet in 1988 and spread extremely fast. Interestingly, it combined three types of vulnerabilities. A buffer overflow in fingerD, which injected shellcodes and commands, right, to gain code execution on the host system, on the target system. Debug mode in sendmail, which turned the most commonly used email daemon at the time into debug mode to execute arbitrary commands, and an attack against users, a dictionary attack with frequently used usernames and passwords, trying out different kinds of combinations of usernames and passwords that were stored. Oddly or unfortunately, the worm itself was buggy. So whenever it infected the worm, the worm was supposed to detect, hey, I've already infected that system, so I'm just going to leave it alone and continue attacking other systems. But this detection routine was actually faulty, and so the worm kept reinfecting the same system again and again until it used up all the resources and the system crashed. If you're interested in knowing more about the Morris worm and reading through its source code, I do encourage you to go read through the source code on this blog post, which is extremely interesting, right? So even 35 years ago, there were issues with that were exploitable on these systems, and this was the first widespread use of a worm that took down large parts of the internet. Today, the things have changed, right? Most bugs are no longer as trivially exploitable as back then, and attackers often, or attack groups often have 10 to 100 people to develop end-to-end attacks, which requires quite a bit of additional effort. Interestingly, if you look at Chromium, there's a statistic that was just recently released. Around 70% of high-profile security bugs are memory unsafety problems. There's different kind of issues with C and C++ pointers. Half of these are used after free bugs, right? So these low-level issues remain a big issue today, right? So they are still the same bugs as 35 years ago that allow exploitation in Chrome, but the attacks have gotten quite a bit more sophisticated, right? So it's still the same type of bug that allows the exploitation, but exploitation has gotten quite a bit harder. It's not just low-level software that is buggy, but high-level software is buggy too, right? I'm just showing here an example of the OWASP top 10. These are attacks, the most common attack vectors against against online systems or web systems. And we'll go into detail between them in one of the dedicated case studies. Now, why is security hard? Right? And I could talk for hours about the hardness of security. But one part is definitely the human factor, that there's a lot of humans working together on potentially large software project, and the limited amount of scope that a human can keep in mind, right? When you're using a module, you may not know how the interactions behave with all the other modules and what the abstractions are across all the other modules. And these abstractions for the APIs may actually break down. You may not be, when you're changing one module, you may not be aware of all the consumers of that module, of all the other parts that are using your model. The concept of weakest link is also quite severe, right? As a defender, we need to protect against the exploitation of all vulnerabilities, whereas an attacker only needs to find one vulnerability that is exploitable. So there's an inherent unbalance between the attacker and the exploiter and the defender, right? The defender needs to protect against the exploitation of all bugs, whereas the attacker only needs to find one bug that is not sufficiently protected. Performance is another aspect, right? Security usually costs some additional resources, as in mitigations require time on the user's machine when they are being executed. Testing requires cycles on the developer end. Also, it may be hard to develop user-friendly security mechanisms. And we may not necessarily have the resources, as in time and money, to develop sufficient amount of software security systems. What are some of the best practices that you would want to look into? Well, it's not that hard, right? We should properly design software. We should have a clear documentation that captures the design and implementation and ideally has APIs and abstractions very well defined. We should leverage frameworks, right? Don't re-implement functionality that you can use from somewhere else, especially if the somewhere else is already verified or certified. We should do sufficient code reviews to get rid of any of the remaining bugs. Rigorous security tests in addition to the unit tests that test functionality. So we should not just test functionality, but also security. Like, does it accept and produce the right result when we supply the correct functionality? But does it also protect against misaligned requests or bogus requests? If possible, formal verification for any components that can be verified. So for example, code snippets, protocols, and whatnot. And also extensive testing for all the other components. For large companies, we need to consider red teaming software, where attackers will try to attack the target software, and also offering bug bounties. Right? So these are all security best practices. You may not have heard of all of them. We'll go through many of them that are more software centric, so that you can actually bring them in and start using them when you are developing software. And also others are for inspiration for you to focus on. What are the course goals? Well, software running on current systems is often exploited by attackers despite many deployed defense mechanisms and best practice for development. Here we want you to understand the state-of-the-art software attacks and defenses across all the different layers of abstractions, right? And this is one of the things that excite me about security. Security is not just one layer, but it hops across all the different layers, from programming languages to compilers to runtime systems to the CPU down to the ISA instruction set architecture and the operating system. And we have to understand a sufficient amount of detail across all these different layers. There's a couple of course non-goals. I don't want you to learn 10,000 definitions by heart. I don't want you to crunch towards a CISP certification, and also don't want you to understand the 58 different Linux kernel heap allocators and their data structures that are out there, right? So the goal of this course is to have a sufficient understanding of software security, attack vectors, and potential issues that happen. You should learn and understand the causes of the common weaknesses, identify security threats, risks, and attack vectors, reason how security vulnerabilities can be avoided, evaluate and assess security best practices and defense mechanisms, be aware of limitations of existing defense mechanisms and how to avoid them, identify security problems in source code and binaries, assess the associated risks, and reason about severity and exploitability. When you are given a piece of source code or a project, you should assess the security of the underlying source code. As course material, we will use Moodle for communication, and I encourage you to go read the corresponding chapters in the textbook, Software Security Principles, Policies, and Protection, which is available free online, and you can access it on the link on the page. Whenever I give this course, I get asked about where we get our security news, and full disclosure is one of the interesting lists where security vulnerabilities are often discussed. So this is a mailing list that you can follow, and a lot of the information security folks are on Twitter and more recently Mastodon. So you can follow me and some of the others that form this circle to learn about different kinds of vulnerabilities and potential issues. There's also academic conferences where you can read interesting papers. There's Oakland, Usenix Security, NDSS, and CCS. And if you Google for these conference names, you will find the major pages, and you can access the different papers there. What I also encourage you to attend are hacker conferences. These are more informal conferences where you will learn about the latest exploitation techniques and also much more focus on a given bug. Whereas academic conferences will focus on new techniques to protect against exploitation or generic exploitation techniques or bug finding techniques, hacker conferences will tell you in a flashy way how a single bug will be exploited and how to take over the whole system. Right, so having a good balance between the two types makes this an interesting and playful environment to look at. And with that, this was all of the introduction. I leave you with a picture from Hackers, an amazing 90s movies about hackers and their key slogan, hack the planet. So as a summary, software security is the area of computer science that focuses on testing, evaluating, improving, enforcing, and proving the security of software. Your goal is to identify common security threats, risks, and attack vectors of software systems, assess security best practices and defense mechanisms, design and evaluate secure software, and all in all, the goal of this course is also to be excellent to each other, understand security issues, and after all, have fun. Thank you.